this chapter, so first lecture in this chapter over what is known as intermolecular forces. And so intermolecular forces basically is just a fancy word for saying the attractions between two molecules. So if you got two molecules, what are the attractions between them? And so we're going to examine 4 different types of intermolecular attractions. We'll look at one called Vander Waals forces, also known as London dispersion forces, and also known as induced dipole attractions. And then we'll look at what's known as dipole attractions. So hopefully you understood what we talked about in the last chapter, what dipoles are. So this is one area where chemistry can be a difficult subject, because if you don't understand something in one chapter, you have problems in the next chapter. So you have to understand the previous chapter to understand this chapter, because you have to understand, for example, what a dipole is. And then we'll talk about what's known as hydrogen bonding and ion dipole attractions. So again, if you don't understand what a dipole is, you got a hard time understanding half of this chapter. Okay, so these are arranged in order of strength. So these are the weakest and going down to the strongest. So hydrogen bonding and ion dipole attractions are much stronger than Vander Waals attractions, and dipole-dipole attractions are stronger than Vander Waals attractions. So we'll talk about them in that order. We'll talk about Vander Waals attractions first. So if we take 2 molecules, for example, so F2 and I2, so do these molecules have a dipole? And the answer is no, they do not, right? So is any atom partial positive or partial negative? And the answer is no, because they're the same atom attached to each other, so same electronegativity. So the electron density so you have symmetrical electron density in the molecule, right? That is until so as 2 molecules approach each other, then what's important to recognize is at some point their electrons will repel each other. So as these 2 molecules get closer and closer and closer to the space, eventually their electrons will repel each other. So when they're really close in space, then their electron density is no longer symmetrical. Then now the electron densities are distorted. And so the electrons on one molecule will repel the electrons on the other molecule, causing them to shift to one side or the other. And so now there is partial charges, right? So now one side of the molecule would be partial negative, the one with high electron density, and the other side of the molecule would be partial positive, right? Because there's not much electron density on that side of the molecule. So on the right side of the molecule, so the nucleus of the atom is exposed, so there's positive charge density there now. And so now there is a dipole. And again, we write the dipoles from positive to negative. And so this dipole is called an induced dipole, right? Why is it called an induced dipole? Well, what does that word induce mean? It means to force it to happen, force a delivery to happen. So an induced, you can induce a delivery. So same in chemistry. In this case, you can induce a molecule to have a dipole. One molecule can force another molecule to have a dipole. And so now there's an attraction between the molecule. So why is there an attraction between the two molecules? Because positives are attracted to negatives. And so that type of attraction is called an induced dipole attraction. Or it's also called a London dispersion forces. They're also called Vander Waals attractions. So the same thing would happen in I2 when two of these molecules get close to each other. Then their electron density will be distorted. And so now one side of the molecule is partial negative, and the other side of the molecule is partial positive. So there's a weak electrostatic attraction. So all of these intermolecular forces that we're talking about are electrostatic attractions in nature. Positives are attracted to negatives. Okay, so they both then now have a dipole, an induced dipole. So they both experience induced dipole attractions, but are they the same magnitude, or is one of them stronger than the other? And so to answer that question, whose electron density is more distorted, F2 or I2? So these dots that were shown and the bonds that were shown are the valence electrons, right? So for fluorine, its valence electrons are 2s2, 2p2, right? Those are 2p5. That would be its 7 valence electrons. And for iodine, so if we look at the periodic table, so it's fluorines in 2p, chlorines in 3rd period, bromines 4th period, iodines in 5th period. So iodine would be using 5s2 and 5p5. That would be its 7 valence electrons. So whose electrons would be easier to distort? Electrons in the 5th shell or electrons in the 2nd shell? And it would be iodines, right? Because those electrons are further from the nucleus, so they're less tightly held, so it's easier to distort them. Right, so I2 has greater induced dipole induced dipole attractions. And so the significance of that is that the more molecules are attracted to each other, the more their physical properties will be affected. So physical properties like we'll talk about boiling point, we'll talk about solubility in particular, we'll talk about viscosity. So we'll talk about several different physical properties, and the greater their attractions between molecules, the more those physical properties will be affected. So this is reflected, for example, in the boiling points. So if you go down the periodic table, F2, CO2, Br2, I2. So F2's boiling point is negative 188 degrees Celsius. Chlorine's negative 34 degrees Celsius. So they're both gases. Bromines is 59 degrees Celsius, so it's a liquid. And iodines is 184 degrees Celsius, it's a solid. And below iodine is AT in the periodic table. Its melting point's 37 degrees Celsius, so it's also a solid. So molecules that are not very attracted to each other are going to tend to be gases. But the more molecules are attracted to each other, they would liquefy at some point, and if their attractions are strong enough, they would solidify. And so the fact that I2's induced dipole attractions are stronger, it's going to have a higher melting or boiling or melting point in this case. So if we took another example, so if we took these molecules, And let's add another molecule to the mix. So 1 carbon, 2 carbon chain. So this would be methane. 2 carbons is ethane. 3 carbons is propane. And 4 carbons. So if we put 4 carbons in a chain, then that is butane. Okay, so which of these molecules will experience greater intermolecular attractions? So first of all, do they have a dipole? Is any atom partial positive or partial negative? And so if you remember how to determine partial positive and partial negative, it's based on electronegativity differences. And so in the previous chapter, we looked at the difference in electronegativity between carbon and hydrogen. So carbon's electronegativity is 2.55, hydrogen's 2.20. The difference is 0.35. And if you remember, that's a non-polar. So all CH bonds are non-polar covalent bond. So no partial positive or partial negative. So again, technically carbon's slightly partial negative and hydrogen is slightly partial positive, since carbon's a little bit more electronegative than hydrogen, but the difference is so small that we just ignore it. So no partial positives, partial negatives in these molecules, so basically none of them have a dipole. So what does the electron density look like in the molecules? So for CH4, it's a pretty spherical molecule. And if we go to the opposite extreme, so if we go to the C4H10, then its electron density looks something like that. So it's kind of elongated molecule, so it's more oval shaped. So basically no dipole, no partial positives and partial negatives until 2 molecules get close to each other in space. So if we took 2 CH4s and those molecules get close to each other in space, then again at some point the electron densities will repel each other. So we can just exaggerate it, just draw some highly distorted blob to represent the electron density. And so now you have a surface that's partial negative and a surface and a side that's partial positive. And then if we did the same thing for the other molecule, so when 2 of these molecules get close to each other in space, then if we look at their electron densities, so it will be distorted towards one side again. So now one side is partial negative, and one side of the molecule becomes partial positive. So in this case, the bottoms of the molecules are partial positive and the tops of the molecules are partial negative, just because that's the way I distorted the electrons in the molecules. It could go in the opposite direction as well. Okay, so now if we compare those 2 molecules, because those are the 2 at the extremes, from 1 carbon to 4 carbons, if we're just comparing those 4 molecules. So which 2 molecules would be more attracted to each other? So these 2. So positives attracted to the negative, or positive attracted to the negative here. So which of those attractions is going to be greater? it's going to be the molecule butane because there's more surface area. So there's a greater number of attractions, right? CH4 molecule is pretty spherical, so if you had two spheres there and they come in contact, you know, how many points of contact are there between two spheres would basically be one point of contact. Whereas CH4 or the C4H10 butane is a linear molecule, so when two of those come together in space, there's lots of contacts between them. So the sum of all of the intermolecular attractions is going to be much greater. So two butane molecules would be more attracted to each other than two CH4 molecules. So CH4, CH3, 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 CH2, CH3, and the butane, CH3, CH2, CH2, CH3. So again, this is reflected in the physical properties like boiling point. If we look at the boiling points of these molecules, you know, which one's going to have a higher boiling point would be the one that has more intermolecular attractions. So butane. So CH4 has a boiling point of negative 161 degrees Celsius. What's a gas at room temperature? Ethane. So if you just extend the carbon chain by 1, its boiling point's negative 88. So significantly higher than CH4. If you extend the carbon chain by another carbon, propane, boiling point's negative 42, and butane negative 0.5 degrees Celsius. So the basic point is, so the basic point to remember is that as you increase length of the carbon chain, then boiling point increases because more intermolecular Vander Waals attractions, or London dispersion forces, or induced dipole attractions, right? All the same. Okay, and so the last point to make here, so it's kind of annoying to draw molecules like this. It takes a lot of time. So there's a much easier way to, so this is what's known as an expanded structural formula. It shows all bonds. There's a much easier way to draw the molecule, and that's to draw it like this, using what's called a line formula. So end of each line equals a carbon, and every break in the line equals a carbon, right? So that's a carbon, because that's a break in the line, that's a carbon, that's a break in the line, and that's a carbon because that's the end of a line. So that's a 4-carbon chain, just like on the one on the left is a 4-carbon chain. And when you draw a line formula, you don't have to show the hydrogens on the carbon. It's just assume that they're there. And so how do you know how many hydrogens are on each carbon? Because carbon likes to make 4 bonds. So each carbon has enough hydrogens to complete 4 bonds. So if we take that molecule, all right, so this carbon has 1 bond to the carbon shown, right? It's got that 1 carbon attached to it. So it needs 3 hydrogens to make 4 bonds. Whereas if we take this carbon, has 2 bonds to C shown, because that carbon and that carbon is attached to it, so needs So it needs 2 hydrogens attached to it. All right, so that's a CH2, and then this would be a CH2, right? Because that carbon's got 2 carbons attached to it, so it needs 2 more hydrogens. And then that carbon only has 1 carbon attached to it, so it would need 3 more hydrogens. So basically at the end of every line, is a CH3. And the breaks in the line in this case are CH2s. Okay, so that's a little bit of introductory organic chemistry for you. So for those of you who go on to organic chemistry after this, you'll be drawing line formulas all the time on organic chemistry. Okay.